All right, so I'm going to go through all chapter 7, basically from 7.1 all the way through 7.5. We've covered everything. We're going to try to put this in one semblance. I'm going to record it. I'm going to go quite fast. This should all be reviewed. All right, this should all be reviewed. And this will put the nail in the coffin of every skill we need for calculus. Starting with that, anytime today I use g of x, we're going to take that to be the inverse function of x, okay? And then we know if I can do an inverse, then we know that f of x had to be 1 to 1. Otherwise, we couldn't take the inverse. So an example would be f of x equals 4th root of x minus 2. And again, 4th root of x minus 2 is going to look something like this. And we know by looking at this curve that it's 1 to 1, meaning that for every input of x, there is one and only one y value. Okay? So a parabola fails, right? A parabola fails because if I say 4, for an output, there are 2 inputs, 2 or negative 2. I teach this in pre-calculus as 1 to 1 passes a horizontal line test. All right? If I want to solve for the inverse, I have to solve for x. And if I do that and don't break any rules, we can always find the inverse function of this. But now here's the problem immediately. X plus 2 to the 4th, right, is a parabola shape. Well, the inverse can't be that. So the thing you got to remember before, after, or while you're doing inverses is the first thing you should be doing here is taking the domain and the range. And when you take an inverse, not only do x and y flop in the answer down here, but the range and domain will flop and follow. So this gets a domain of negative 2 to infinity, and the range becomes 0 to infinity. So if I was to do that graph up here, it would look like that. And it's a mirror, right? And I'll call this g of x now. And it is a mirror across y equals x every time. And it's this mirror relationship that allows us to find the derivative of the inverse without having to take the actual inverse of a function, so long as we know it's 1 to 1. So if we flip to the next page on that, all right, we have to kind of stick with this fact. F and f negative 1 are reflections of each other, right? And this is why this derivative that we talked about works. And we know that f is continuous. That makes it differentiable, right? Thus, the inverse is continuous and differentiable. And therefore, we found by doing the mirror that we could find the derivative of an inverse at A by doing the reciprocal of the original function at the g of A value. So I could do the proof. It is in the book if you want to read it. I'm not going to do it again. We did it as the cotangent tangent proof before. If I look here, we could find, if I tell you f of x, and again, often we use functions that have easy values because we don't want to get bogged down in math. So here is a function, right? And 2x is a polynomial. Cosine of x, all right, is cosine of x is our trig function. Now the question becomes, is this 1 to 1, right? But you got to remember, it is 1 to 1 because we are adding these two functions together. 0, 0, I put the origin in and I move that curve a little bit, that curve is going to go up, and when you add them, it's going to go up and away. All right, so it does stay away. It is 1 to 1. So we want to find, then, if we know it's 1 to 1, we can do the inverse. We can find the inverse function at a value. And again, we want a value that's easy to do. So we'll do it at y equals 1. Mainly so that you can find the input. When we see this, this is not an x value, right, of f of x, the move function. This is a y value of the function. And again, I found that personally to be confusing when I was learning this stuff. I look up at the function, and I always guess and check values. 0 is one of the ones I guess and check, and I find out that f of 0 is 1, because 2 plus cosine of 0 is 0 plus 1. Then I know that g of 1 is 0. And once I have all that information, I can easily do the derivative now up here. And it is plug and chug. And I would probably write the derivative below this function right now. Derivative of cosine is negative sine, right? And I would go g prime of 1 equals 1 over f prime of, and I'll write g of 1 for a second, but that is 1 over f prime of 0. I would probably do this. I would probably just go down here and go f prime of 0 equals 2 minus sine 0, which is just 2. And we just found the inverse function at a value. And we did this the other day again. And that takes care of all 7 1. All right? I don't want to go through the proofs again on any of the other stuff. So 7.2 brings us into these rules. That the derivative of e to the x is e to the x. The derivative of any other a to the x function is ln a as a coefficient times a to the x. And this works for e to the x. If you want to do e to the x with this formula, you get ln e times e to the x, but ln e is 1. So it does work, you know, if you want to memorize 1. And again, I can mix these in. We want to do it. Try to find a good example here. Yeah, here's a good example. So there is actually a book example of this. Or a problem in your textbook. Let's get them both in the same one. But here's the first thing. What kind of rule do we have to have for this one? Product rule. It's 2x. It's 2 different things. So I'm going to call this f. I'm going to call this g in my head, right? And we know f prime g plus g prime f. So I do g prime of x. The derivative of 2 to the x is ln 2 times 2 to the x e to the x plus g prime is just e to the x. Okay? And this is typically how you're going to see tests in calculus, right? They're going to mix these in to be able to see product rules with quotient rules, all right, or whatever. And again, we've known this rule. We've had this rule a little bit come up. The one thing we haven't done yet is this. All right? A definite integral, correct? A definite integral. So at the bottom, I want some value. All right? And we know only one fact, right? The fact we know is this. So if I have e to the x and I integrate, it's going to be e to the x. There are 2 distinct ways to do this. I don't know how good you guys are becoming with guess and check, all right? We'll do that the second way. I would probably guess and check this one. I would not do a u substitution long term with this, because I know the derivative of e to the 3x is 3e to the 3x. You know what I mean, guys? But we'll do the u substitution. I'll say u is equal to 3x. I'm going to say du is equal to 3 dx, right? Because that's the derivative of u equals 3x. And I notice that I'm going to need to have a 3 with my dx, right, to make this work. But I can't just put a 3 here. I have to put a third here. And then I'm going to do this. I got 1/3 integral of e to the u du. All right, guys, what's the integral of eu? EU. And there's no plus c, so it's going to be EU. It's got to be integrated or evaluated. Now, everybody, you notice I left numbers off, right? I have two choices here, and I want to be clear about this. At this point, I either have to do this black step and replace u back with 3x, and I can say that's from 0 to 3. And I still have to do the evaluation here. Or here's what I'm going to do. I'm going to change the limits of integration to 0 to 9 and not resubstitute 3x for u. And then I can do this, then I can quickly do the red integration in 1 second. It's 1/3 of e to the 9th. E to the 0 is 1, and there's my answer. Now, would I get the same answer for the black one? Absolutely. But a lot of times, it's easier to change the limits of integration to match your u and not resubstitute. And that is allowable on these e to the x problems. All right? Otherwise, you do have to substitute back. If you want to stick with 3 and 0, it has to be with respect to x. These limits were x values, not u values. All right, so I got this, right? Integral from 0 to 1 of x to the e raised to the negative x squared dx. This is definitely one where, again, with practice you don't have to, but this is probably more of a u substitution problem. I can see right away that the derivative of negative x squared, right, is going to be negative 2x. So I'm going to do two things. If I was rewriting this problem, I would put the x here right away. And again, well, I'll just do the u substitution. U equals negative x squared. Du equals negative 2x dx. Well, I already had the x, thank goodness, because I can't add x's. That x wasn't there, this wouldn't be doable. I need a negative 2, which means I need a negative half. All right, and then I'm going to change the limits of integration this time immediately to u. So I'm going to plug 0 into negative x squared, and I get 0. I'm going to plug 1 into negative x squared. I'm going to get negative 1. All right. I'm going to write this as e to the u du, and I'm going to do this quick change. Right, because I want to integrate in order. You notice the negative in front of the half has now disappeared. This is 1/2 of e to the u then, from negative 1 to 0. So e to the 0 is 1 minus e to the negative 1 is 1 over e. And that's our answer. Okay? If you can see this, all right, one of the things I can do, all right, instead of all this u substitution stuff, I group all this. This is probably what most students do. If you're going towards Calculus 2, all right, and you're going to try to get through, one of the things I do is, listen, I see that the derivative I know it's got to be this. You guys agree? So I'm going to do this. Now, the only thing wrong right now is I don't have the right coefficient. So I'm actually going to take the derivative of this on the side, or in my head, depending on how much calculus practice you're willing to do. So in my head, I know I get 2x. When I take the derivative of this, the derivative of e to the negative x squared is e to the negative x squared. And then I get to do the chain rule and get a negative 2x. When I look up at the original problem, I see that I am short. Well, no, I got the x. See, I got this stuff right here. What I'm missing is just that number, negative 2. So somehow I got to put something on my black equation, get rid of the negative 2. Now, if I take the derivative of this black equation, the negative 2's will cancel, and I get the same thing. And I pull the negative half out, and I get e to the negative 1 minus 1. Now, everybody see if you distribute the negative. Get the same answer, right? Now, I probably would be pretty lazy, guys. I probably would just have stopped here. I'd probably write that as 1 over e. I'd take it both ways. The only reason you have to be able to do this work to these things is in case it's multiple choice. All right? And these are just chain, or these are chain rule integrations, right? Use substitutions. As they get easier, a lot of times we can see them. So if I give you an easy one, let's do a indefinite. So the only thing is no limit integration. If I tell you cosine 3x dx, you could do this as a use substitution, but the argument never changes, right? So you got to think to yourself, what gives me cosine when I take a derivative? Sine. So it's got to be sine 3x, guys. And when I take the derivative of sine 3x, I get cosine 3x times 3, right? So I better just put a third here, and I'm done. And I can avoid use substitution. Does my derivative of 1/3 sine 3x give me cosine 3x? Yeah. All right? As you practice, this gets easier. Seven 7.3 in our textbook is just a review of logs. All right? And the only thing I want to go through real fast is we should be able to handle that when you're adding logs, right, you're adding exponents, you're multiplying bases. When you're subtracting exponents, because log A U is an exponent minus log A W, you're dividing. And again, I'll show these two rules this way. X squared, X cubed is X5, guys. 2 plus 3, right? You're multiplying the bases. X7 over X4 is X3, right? 7 minus 4, because you're dividing. All right? The last one, and this is the one usually you guys, we tend to screw up, is that when you take a power to the power on the power rule, you actually are multiplying exponents so that power can come out. The example for that is X3 to the 4th. That's not X7, it's X12. But the one that a lot of times we forget is change of base, all right? And if I have log A to the X, you can write this as log base 10 of X divided by log base 10 of A, right? And students always say, yeah, you just keep it in order, right? Juda, we typically talk about this in the context of that you probably wouldn't remember this rule very often. And if I have log 3 to the 7, I know there's no power, right? That gives me 7. 3 squared is 9. 3 to the 1 is 3. We talked about just setting this equal to x, right? And writing it as 3x to the 7th power. And then taking the log of both sides. And then, yeah, and then you can see that the change of base formula just pops out of this thing. So you take log 7 divided by log 3. Typically, we need this just to help us do log problems or ln problems, okay? And we should know that log, just like Kyle was saying earlier, that ln of e is 1, well, log 3 of 3 is 1, or log x of x is 1, right? That when you have a base and the result's the same, it has to be 1. And if any number, and I don't care what this base is, this is always, I don't care what the base is, if the result is 1, the exponent is always 0, all right? And that was pretty much all of 7.3, which takes us into derivatives of 7.4. And again, I'm not going to go through the proof of them. And everybody, this handles our problem of integration because you guys are really good at x5 dx, right? You add 1, you go x6 over 6 plus c, right? And even if I change this to -5, you guys don't care, right? You can get x -4 over -4. Well, the problem we've ignored and the problem that we never dealt with is if you have -1 here, and you try to add 1, you get x0 over 0 is that rule, and obviously that doesn't work. Okay. First off, the derivative of 1 never gives you x -1. Secondly, you can never divide by 0. So it is our ln function that fills this gap, and it's, you know, the natural thing of math. And the integration of 1 over x dx then is ln, and we know that we can't have a negative number of logs, okay? We can't have a negative, so we have the absolute value of x. Chain rule, all that stuff stays the same. Product rule, you name it, does not matter. All right. Where it comes in handy is on large functions that we do not want to deal with. So I'll use these two rules. Everyone, this is a function we can't do without our log rules. All right? Because first thing you should catch is you got x in the bottom, x in the top. We have rules. We are really good with x in the bottom, right? We love x cubed. And while we might not love 3 to the x, we just reviewed that rule. Did we agree? But now we got them in bold, and you can't live there. So I always say take the log. And what happens here then is what? It goes from a problem we can't do in black to when you use the properties of logs, we have now created a problem we can do the derivative of. Because what's the derivative of ln y? 1 over y. I'll put the dy here so we understand it. On the other side of the equal sign, what do we got? We got a product rule. I'll do the square root of x first. I get 1/2 x to the -1/2 ln x. Oops. Plus square root of x times 1 over x, right? And those both are what? Those are both done with respect to dx. And then if I divide both sides by dx, I got 1 over y equal times dy dx, which is y prime, equals. And I would probably simplify this a little bit. I'd write ln x over 2 square roots of x plus 1 over square root of x. And everybody, you guys see that I have y here now, so I multiply by y. And I probably would do this first. Almost for sure, if this is a calc problem, you get to a single term. So I have 1 over y prime equals ln x plus 2 over 2 square roots of x. But what's y, guys? If I multiply by y, I can put y here, but y is x squared of x. So when you have functions like this, they actually end up in the derivative with the logs, all right? This is out of 7.4. We'll be practicing more of these, but these are those log problems, okay? And it's the only way to take the derivative of the black is to put it in terms of logs. Now, could you do this in terms of log? Yeah, I suppose you could. You don't want to. ln is a much powerful way to handle the derivatives. We do have a rule for logs if we want to do that. And we learned this because it's converting. The memorized rule for logs, if you use log, I'm going to write just like the book, so you can use that. Log AX, they use A. All right, is that it's 1 over X ln A. Everyone, the reason the ln A is in here is because if you want to do this, they actually make the conversion to ln. We really only, this is just a shortcut to memorize through. I don't actually have it memorized, just like I don't have cotangent memorized that well. Every time I come up with it, I derive it. I derive this every single time too, because everyone, could you say this? Does that make sense, everybody? And then could I say this? And then I take the ln of both sides, and I'm going to drop the y right away. And now if I take the derivative of both sides, derivative of y is y prime, ln A is a constant, derivative of ln x is 1x, and you can see that y prime is 1 over x ln A. All right? I don't purposely, I do not like memorizing. I try to minimize my memorizing. I have to derive it every time. Again, it depends on how much math you're doing, all right? But anytime we have a log, then we can use that. And it doesn't have to be pretty, all right? And it can be chain rules. The book example, the first book example on this one is they do this. Log 10. Ugh. Log 10 of 2 plus sine x. All right. And again, our rule that we just talked about, I'll put it up so it's underneath it. Log AX. 1 over x, because there's the ln portion. And then there's the constant portion. Everyone, you take a look at this, you're going to have a chain rule, right? You got log 10 crap. So in red, this is our rule. It's 1 over then ln 10, you guys agree? Times the stuff, 2 plus sine x. But here's the problem. Anytime you say stuff, you have to take derivative of stuff. Derivative of 2 plus sine, I'll probably write the 0 so you make sure you understand it. Derivative of 2 is 0. Derivative of sine is cosine. So the answer to this problem, when it's simplified, is just cosine x over ln 10 times 2 plus sine x. All right, head towards Calc 2. This gets to be not a whole lot of fun to integrate. Right? I mean, if you can take the derivative, right? If I show you this and I say, hey, here's the, you know, I want to integrate this. Well, right now we know at least this is the answer. You guys agree? So at the bottom, because every time we do the chain rule, so why does it go up here, right, versus with the bottom? Because it's always the derivative rule, and I know this is a little bit mucky. If we talk about f of g of x, we take f, we want the derivative of that function. It's f prime of g of x. Then outside, it's g prime of x. So this was actually out here, right? It's over 1, so it always folds into the numerator, okay, every time. my goal was to get through all 4 lessons today. And we did, and we got to practice some of this. What? That would make it? Well, we've done all this. We've done all this. Maybe only once.
Doesn't mean we're good at it.
Doesn't mean you're good at it if you don't practice outside of my time, right?
That's right.
But we've done all this once. I tell you what, I got one more time to throw one more on here. Let's find one that's really ugly. No, I'm not sure. Takes about 1 minute. Here's a good one. And everyone, every time you see x in the base and x in the power, what do you got to do? You've got to take the log. And don't take the log. You got to take the natural log every time. You should really try to avoid taking logs. So the first thing you got to do on this thing is this. And does everybody know why this x comes down? The rule, the power rule, right? It's the power rule of logs. It has to be able to come down because when you multiply. And this is what gets students, because now it's implicit differentiation. Guys, the derivative of ln y is 1 over y, and that was done with respect to dy. Now, if I divide by dx right now, all the dx's on the other side, I don't have to write. Does that make sense to everybody? On the other side, I got to change, or product rule. Derivative of x, 1. So ln sine x plus x times, all right, derivative of sine of ln is 1, ln x is 1 over x, so it's 1 over sine x. And the derivative of sine x is cosine x. Woofta. All right, so I get 1 over y prime equals a little bit of math, ln sine x plus x times cosine over sine, cotangent x, you guys agree? Right? Because sine over cosine is tangent. And then what? Well, we knew from the start that one of the things that happens here when x is in both, and everybody, this is y. You multiply both sides by y, right? But what is y this time? Sine x to the x power. Now, I know some students can start to see shortcuts here. I don't do them. I mean, I'm really good at calculus. And some of you will start to see the shortcut here, all right, with the y. I always write this out. Because you know this is going to drop in and down here. I get it. And then it's just the derivative of the ln's, right? But I think that's risky. And I think you always want to have it make sense that y is part of this because of this step right up here. All right? We'll practice this next week. But everyone, this finishes. This is it. We might, after this we're done, we might do a little bit of limit work and a little bit of work with Lahav's rule. All right? Lahav's rule. It's a simple rule of limits. All right? In fact, a lot of pre-calculus classes handle it. So, all right.